Good morning, everyone. So thanks for the opportunity to present our research from my lab in the Department of Engineering Science, Oxford. So I'm going to share with you some of the new results, and they're now published. So we got our new equipment around 2019. So in 3 years, we generated quite a few nice examples of studies, which I'm going to highlight today. So my co-authors here, as you can see, Annika Moslin, she's in the audience. You might want to spot her later to ask more questions. And Michele Tricarico, he's attending remotely. So both of them are excellent graduate students, as you'll see later from the results. So let's move on. As a talk outline, so here's what I'm going to cover. So let's talk about what the materials are. Metal organic frameworks have been gaining quite a bit of attention, why they are interesting and what they might be good for. So then we move on to 3 case studies, the first of which is to look at guest-encapsulated metal organic framework, MOF crystals. These are nanocrystals which we have characterized. Then we look at the nanostructured monoliths, by nano-indentation and the effect of stress on the chemical bonds. Finally, if time is permitting, then I'll cover defective frameworks and how we're going to look at the effects on mechanical behavior. So here are the general construction of MOF materials. I'm going to illustrate this using a prototypical framework material called ZIF, which stands for zeolitic imidazolate framework, particularly this guy, ZIF-8, which is a nice exemplar. So although we are in the inorganic session, actually the material, as you can see, is a hybrid. So we got metal components as well as the organic building blocks. So to build a ZIF-8, so you can think of having a metal site, in this instance, zinc nitrogen 4 tetrahedron. So this would be the node. And then you have to bridge this using organic linkages. In this instance, we're using this methyl imidazole linker. And they form this nice connectivity, which gives rise to topology, which has a cage-like structure. So don't forget that we are looking at a material which is crystalline. So this is not just one unit cell. Well, I mean, this is a unit cell which is replicated in 3-dimensional space. So you got a crystalline structure. And the big attraction of such a material, of course, is the volume or the space available at the heart of the framework. So the surface area is huge, typically of the order of thousands of square meters per gram. So if you can put this into context, it will be the surface area of a football field, for example. Accessible porosity also pretty high, of half of the volume is actually vacant. So we can use this for all sorts of things. Just to show that in terms of materials engineering, you can envisage making the materials or shape them into different morphology and also different architecture. So you could start with, of course, single crystal material that are great for basics research. You can think of also making nanocrystals. So these guys could be fused together to form what we call monoliths. So these are millimeter to centimeter size bulk material that are good to handle. And also these nanocrystals could also be blended with polymers as a matrix. So you can make membranes, or you can think of making fibers out of these composites, right? So this was made by means of electrospinning to make polymer composite fibers. Or you can make thin films and coatings on various substrates. Now, the original application targeted was in separations and gas capture, as you could imagine, given its high porosity. But in my group, we are looking at more niche applications. So this is a recent review paper just came out last month, where we talk about trying to trap luminescent guest molecules. So these are fluorophores, very bulky. If you can capture this and host them inside the MOF structure, this can give rise to all kinds of interesting properties and applications. So in optoelectronics, photonics, and smart sensors, for example. So here, just to illustrate a few, you can think of applications where luminescence play a role. So a VOC, volatile organic sensing. You can think of physical sensing, so in terms of temperature or stress and strain or pressure, you see changing in colors of the emission as a function of pressure, so quite fascinating. Chemical sensing, of course, pH, anions, and so on, in bioimaging and also in security applications. So in ambient light, the encoded information is invisible. Under UV, they become revealed. So quite interesting. Let's jump into my first case study. So the work was performed by Annika here. So as far as we are concerned, this is the first study on MOF materials where we have used the tool very comprehensively and rigorously to probe the physical and chemical behavior of a single crystal. So this is a ZIF-8 or UIO type material, which we reported in this manuscript. In this set of slides, I'm just going to talk later about ZIF-8. But the illustration here is for a UIO material with a rhodamine B, which is a fluorescent red fluorophore. So they could be either sitting inside the cage, truly as illustrated here, or they could be sticking outside, just attached to the surface. So in or out, so that was the question, really. Of course, out, whilst it's functional, there are some limitations, being easy to wash away, photo degradation, so on. Inside has its advantages. So now, let's look at the host nanoFTIR first. So you all know about that. Let's look at the comparison between the different techniques. So experimentally, you can have a bulk powder. So ATR, FTIR spectra are given here from a bulk measurement. DFT is density functional theory calculation. So this is very helpful because it revealed to us what each mode or band means in terms of the molecular response. And nanoFTIR, as you can see, labeled here, or with tag 1, 2, 3, these correspond to the vibrations which are identified here from DFT. So band 1, 2, 3 correspond to out-of-plane linker mode, in-plane, and also CH rocking mode. So these are the characteristic bands of a ZIF-8. But particularly, we are actually measuring this from just a single crystal, which size is about 100, of the order 100 nanometers. So first time shown reliably. How to reveal guest-encapsulation, the next step. So we could have a rhodamine B trapped inside. This is just a cartoon. But it depends on how you make the materials, right? You say a composite, well, you can mix things up. They could form, of course, two-phase material like this. So if we can go in and probe this region 1 and 2, you see that the guests are all these blocky crystals. ZIF-8 is these nanoparticles here. So they are not really integrated, are they? So we want a material which are truly a single phase, if you like. The guest is caged inside the ZIF-8 host. And we have evidence to show that yes, when our materials are prepared in the right manner, indeed there are variations in the spectra which could be associated with a true encapsulation. And this came about not from linear combination of the spectral information alone, because linear combination typically means they are just on the outside or just attached to the surface. We are actually looking at interactions whereby the bands are shifting, or the ratios of characteristic bands are changing. Just for example, if you look at, so what I denoted, we denoted 3 and 4 here. So there are modes associated with CH rocking. And number 4 is the OH bending and so on associated with the rhodamine B guest. So if we take the ratio of this guy to that guy, it's about 1 to 1, but the ratio then went down. So we could, I think, suggest that as a result of host gas encapsulation, the confinement gives rise to such a modification in the vibrations. So now we move on to QCL imaging. So mapping the material at specific wavelengths. So the characteristic wavelengths that we use for rhodamine B, as you can see here. So it tells us that for material that we wash very thoroughly, because we don't want any surface rhodamine B sticking on the outside. So you wash thoroughly. In ambient light, you see that the pinkish solution became clear. Okay, but in fluorescent spectroscopy, they actually lit up. So the rhodamine B actually is still there in the framework, okay, not on the outside or suspended in the liquid. So now, if we probe the after-wash material, you see that the ZIF-8 still remains ZIF-8, which is encouraging, some edge effects, of course. But in the well-washed material, the rhodamine B signature 1470 completely disappears. So we have additional evidence that we have encapsulation in the cage itself. Further evidence obtained from fluorescent lifetime imaging of single crystals. I'm not going to talk about this, but the details are all found in that manuscript. Hopefully you look it up. What we got is mono-exponential decay for one of the example materials, and that shows, again, partitioning of your monomers, and there are no aggregation and so on. Right, let's move to second case studies. So these look at mechanical behavior of ZIF monoliths. So as I said earlier, these nanocrystals could be aggregated, so we get a bulk material like that. So indentation, basically, this is done outside our spectrometer, of course. So it's a different instrument. You have a diamond indenter tip. You can push into your material. And what really nice here is the white light images show this formation of cracks, which lit up very nicely. Not visible, not that easily seen if you just do a height image. And TFM is one of the things that I'm going to show you here. So now, two types of indenter tips were used, Berkovich versus cube corner. The main thing you have to remember is the cube corner is sharper, so the stress concentration under the indented region will be much, much greater than the Berkovich to the cube corner. So then we do a line scan across the indent or the residual indent, and you can see the highlighted boxes correlate to the spectrum or the spectra that we have pulled out here. So in the red, the yellow bands, so you see the broadening as we are approaching the inside of your residual indent. These are suggestive of things like structural amorphization or just distortion of the framework. And then remarkably, we see some enhancement in intensity. For this 1311, I'm going to tell you later that we have done density functional theory calculations, which suggests that this is due to missing linkers. So we have a breakage of chemical bonds. And this happened only for the cube corner indenter, but not for the Berkovich, due to the stress reason I explained earlier. So here, just to show you the contrast or the very nice microstructures or nanostructures, to be precise, which you can obtain using tip force microscopy. Thank you. This is equivalent to the Bruker's, QNM peak force, if you like, but near-spec implementation is called TFM. If you have the height image, you see that is not so fascinating, but once you do the TFM, the grain boundary is completely lit up. And this gives us further confidence that the mechanism has to do something with the grain boundaries. Hereby we suggest the grain boundary sliding. Right, I need to wrap up, so no time for case study 3, but this is, again, Annika's work. Going to appear on the front cover. So what stimulated this idea, you can talk to her and she'll tell you all about it. Basically, we're going to look at crystallization and how the amount of defects and more locally, the changes in the framework can be understood using a combination of nanoFTIR as well as DFT, okay? So, and TFM, again, if you have, I say, calibrate this correctly, you could pull out quantitative information, but it's not straightforward. Edge effects and so on need to be considered, of course. Take-home messages, 3 bullet points, first of which is nanoFTIR. We can now really probe locally to look at things at the single crystal level, looking at gas positions in this exemplar, whether it is inside or outside. That really matters for the materials which we claim as a composite. Now, nanoFTIR and DFT, so experiments and theory combined, is extremely powerful. So this elucidated the mechanisms and also some of the structural changes or vibrational modes which you cannot get just from experiments alone. And thirdly, I think this is quite underused at the moment. TFM is a wonderful technique, but still, there are still challenges to get quantitative information out of. Really nice to do mechanics and also just to understand or look at grain boundary effects. Right, thanks the funders, including NIASPEC, that enabled this work, ERC especially for the consolidated grant, and graduate students who contributed to the research I spoke about here. So thank you very much.